Okay, so I want to continue on here with section 5.3, which basically, like I mentioned yesterday, is periodic trends. So we have three left. We're going to go through electronegativity, then ionic radius, or the sizes of ions, and then wrap up with electron affinity. So again, you're going to follow these on the periodic table. A couple of these aren't quite as straightforward as ionization energy and atomic radii with what you did yesterday. But you can still make some predictions based off the periodic table or based off the element's location on the periodic table. So the next trend is electronegativity. So here is the definition of what electronegativity is. It basically means in a compound that different atoms have abilities to sort of pull the electrons closer to them in this particular compound. So as you can see, the actual statement measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. So these can be neutral compounds, they can be covalent compounds, ionic compounds, whatever. But normally we talk about these in terms of molecules and where the electrons are. Because from this, we can determine whether a molecule is polar or nonpolar, meaning is there a separation of where the electrons are located. So here's a periodic table of electronegativities. I know the trends are labeled on there, and you can see that as you go across the period, you have increasing electronegativity. And as you go down a group, you have decreasing electronegativity. So in terms of how that relates to other trends, it's the same as ionization energy and the opposite of atomic radius or atomic radii. Our greatest electronegativity value is right here. That's fluorine at 4.0. So fluorine, when it's in a compound, it has the best ability to attract electrons. Okay, so again, the trend is, and we'll see these on the next page, as you go down a group, they tend to decrease. As you go across a period, they tend to increase. Okay, so here's your trends. Your electronegativity trends. Here's your period trend. It increases across the period. And your group trend, it either decreases or remains about the same. They're pretty similar in terms of the group and what they can do with electrons. If I just back up here, you can see, especially leave hydrogen out of there, but especially the alkali metals, they go from 1 to 0.7. So there's very little change. These elements down here have a very small ability to attract electrons, and the elements up here in the upper right have a pretty large electronegativity value. Okay. All right. So that's electronegativity. Let's move on to ionic radii. A couple of terms that you need to know. One is cation. Okay. That is a positive ion, and that is an atom that has lost one or more electrons. The trend really that you need to know is that when you lose electrons, the atom gets smaller. Not only because of less electrons, so the electron cloud is smaller, but you also have more protons than you do electrons, so it pulls it in even tighter in that regard. So when you form a cation or a positive ion, it gets smaller. And an anion, as you can see, that's a negative ion. That's formed from gaining one or more electrons. And this leads to an increase in atomic radii. Once again, because you're adding electrons, plus now you have more electrons than you do protons. So the atom spreads out. And that just means you have more electrons. Okay, so you have a larger electron cloud. All right, here's just a couple of diagrams, these next two pages, that look at the neutral atom. That's the yellow here with these cations. And here are, these are the neutral atoms, and these are your cations, the blue. So you can see from Li to Li plus, they get smaller, and that is the trend. Okay, that's group 1, or the alkali metals. Here's group 2, or the alkaline earth metals. The gold or the yellow are the neutral atoms, or sometimes called the parent atom. And then you have your cations. You can see they get smaller. Then finally, this is group 13. Again, leaving out the D block. You can see as these lose 3 electrons, and that's their common form, their common cation, because they have 3 valence. Group 2 has 2 valence. Group 1 has 1, so they tend to form plus 1s, plus 2s, and plus 3s. Okay, here's some anions. Here's group 15, or the nitrogen group. It has 5 valence. It tends to gain 3 to become stable, and you can see it gets much larger. Here's group 16, or the chalcogens, the oxygen group. They tend to gain 2. They have 6 valence, so they tend to gain those 2 and get larger. And here's group 17, the halogens. Here they are as their neutral parent atom, and here they are in the green. They tend to gain 1 because they have 7 valence electrons. So really going across the period, the trends aren't like they are with the other 3 we've talked about. Basically, what you need to know is that metals usually form cations. They usually lose electrons. And the nonmetals tend to form anions, okay? So remember your zigzag line, which runs through your p block, that separates your metals from your nonmetals. And then finally, your group trends, because they lose or gain the same number within a group because of the same number of valence electrons, the trend is very similar to atomic radius. They get bigger as you go down a group because you're adding more energy levels. So even if you're losing electrons, there's still electrons at further energy levels, so they increase down the group. Okay. And lastly, our electron affinity. And this really is just the opposite of ionization energy. Ionization energy, if you can remember, was the energy required to remove an electron. Electron affinity is just the opposite. It's the energy change that occurs when an electron is gained. So really with ionization energy, they're forming cations, and with electron affinity, they are forming anions. Okay, so there's 2 ways that this can go. Mostly we only look at the first way here, when atoms release energy when they acquire an electron. So you take this neutral atom A, you add an electron, it forms the anion, but it also gives off some energy. Okay, you'll see in the next slide where there's a little diagram, and these are the ones that are the most red. Okay, the other one is atoms must be forced to gain the electron. So they're what we call endothermic. So you take this neutral atom A, you add an electron. To make that happen, you also have to put energy in. Okay, then again, you get the anion here that forms, but you need to put energy in to make it endothermic. Okay, so here's some trends before we get to that diagram. Higher electron affinities mean the atom is more likely to gain an electron. Okay, and really the halogens tend to have very high electron affinity values because they really want to gain 1 to get 8 valence electrons, which fills out their outer energy level. So they release a lot of energy. It's very exothermic whenever they form these anions. With the p block, it sort of increases across the p block, not across the whole group. Okay, and usually down a group, usually decreases. The electrons are added with more difficulty. Sometimes you see that, sometimes you don't, but that is one of our very slight group trends in electron affinity. So if you look at this last slide, this last diagram, these elements over here, these halogens, they have the greatest affinity for electrons. Okay, and you can see kind of as you go down from that, it gets a little bit less. Gold has a great affinity for electrons. Okay, when it gains 1, it fills its D block. Even the alkali metals have a little affinity for electrons because they go from 1s to 2s. So they fill that s orbital, which makes them a little bit more stable. Okay, so all you really need to know here again is the substances that have a lot of electron affinity release a lot of energy when they gain an electron to form an anion.